Okay, welcome back. This is 8.1 matrix solutions to linear systems. So, what the heck? Let's take a look at it. Right. So, what is this? That maybe that's our first question. Recall having systems such as 2x minus 3y equals 5, and then we'll say 4x plus, I don't know, 9y equals 6. Okay. So I want to solve this, but I want to do it in a new way. And a number of the things we could do, we could sort of multiply one equation by a constant, add equations together column-wise, and then do back substitutions. We're going to encode that now in matrices. So what is a matrix? Well, in particular, we're going to be just working with the coefficients of these guys. And then we're going to put a slash, kind of like an equal sign here, and then 5, 6. Okay. What you're ultimately doing with the matrix is basically the same thing that you would be doing with your system above. It's just it works a little bit differently, so it can be automated. So the first thing you want to do is get a 1 in this position here. This pivot position basically is what they call it. So divide through by 2, I get 1, negative 3 halves, and on this side we have a 5 halves. Okay. Down here we have 4 still, then 9, then 6. Okay, so what is the counterpart sort of to the systems? Well, normally you would just multiply this thing by negative 2 and then add it to this, but we want like a more general procedure. So what we're going to do is kind of put a 1 here and then multiply it to add it to this thing, but we're going to keep this guy kind of the same. Okay, so you can think of what we just did as multiplying the first equation by 1/2. And you would get x minus 3 halves, y equals 5 halves, and then down here we keep it the same, 4x plus 9y equals 6. Okay, so now what I'm going to do is multiply this row by 4 and add it to this row. Okay, so I'm going to multiply the first row by 4, and we'll have a special way of notating all this. So it's going to be 4 times row 1, and then we're I guess negative 4 times row 1, and then we're adding it to row 2. And row 2 is where we're putting the results. Okay, so we're storing the results just like a computer might store information. Right, so the first row now will stay the same. And then the second row, I have negative 4 times 1. So negative 4 times 1 is negative 4. And then if I add it to 4, I'll get 0. Negative 4 times negative 3 halves. So that'll be positive 6. And then finally here, I have negative 4 times 5 halves, which will be negative 10. Oh, and then I'm adding it to these, sorry. So 6 plus 9 is 15. So I'll show you what I do with the equations here in a second. Negative 10 plus 6 is going to be 4. Okay. So in equation land, what exactly did I just do? So I had my original system up here. I'm going to multiply this equation by negative 4. Okay, so I get negative 4x plus, and that's where I made the mistake. I have a 6 here, so negative times negative positive, and then 2 in the 4 is 2. 2 times 3, 6 y's. And on the other side, we'll have negative 10. And then below, 4x plus 9y equals 6. Okay, and what was going here is what happened when I do the addition. Okay, so this would be 0, and then 6 plus 9 is 15y, and then over here I get negative 4. Okay. The next step when you're doing this automated method with the matrices is to get a 1 right here. And what that means is basically you're dividing both sides by 15. Okay, so I'm going to multiply row 2 by 1/15. So row 2. Okay, so 1, negative 3 halves, 5 halves, and here's 0, 1, 4/15. Okay, so if I divide both sides of this, and this sorry, should be negative. Okay. If I divide both sides here by 15, I get negative 4/15, which is this answer here. You have the first one. And then what did we do? We back substituted, but this is nice because what we're doing is sort of back substituting into this formula here. So this records the formula that is most suited for back substitution. Okay, so I'm going to write that x minus 3 halves times y equals 5 halves, and then I'm just going to substitute this thing in here. Okay, so I'll have x minus 3 halves times negative 4/15 equals 5 halves. And then 2 positive 6/15. Sorry, I picked a really bad example to work. Equals 5 halves. And then x equals, we want a common denominator, I guess, of 30. So this is really not working in my favor. 5, 2, 75. So 75 30ths minus 6, 12 30ths will be the result there. So 12, 3, 63 30ths. And of course, we can divide top and bottom by 3, you get 21 tenths. Okay, sorry, I went off the page. Okay, so those are your solutions. In the matrix, we can get this solution by now multiplying this equation and then adding it to this equation. Okay, so with the matrices, what I'm going to do is multiply the second equation by 3 halves and then add it to the first equation. It's basically rows. Instead of equations, we're going to say rows. So here we'll have 0, 1, negative 4/15. And then through the top, I'll have 0 times 3 halves is 0, plus 1 is 1. And then 3 halves times 1 plus negative 3 halves is 0. And then 3 halves times negative 4/15. We get negative 6/15. And you kind of see, that's what we were after. And then we're adding it to this 5 halves here. And we should end up with exactly the same answer that we got doing the back substitution. Okay, so I need a common denominator. I'm doing 15 top and bottom, so 75 30ths. And then 2 top and bottom, negative 12 30ths. Add those together, and you get 63 30ths. And of course, we're just getting the same answer, 21 tenths. Okay. Okay, so what we want to do is automate this process, and basically then if we put it in terms of matrices, we could put it into a computer, and the computer could do all the work for us, and the computer could do bigger and bigger matrices, and that would be much more efficient than paying some poor sap to sit around doing these all day long. Okay. Okay, so, but at the heart of matrices, all you're really dealing with are systems of equations. Okay, so don't let the symbols and stuff intimidate you. All kinds of numbers. Oh, you must have to have some sort of, magical ability to deal with this. No, it's just solving systems of equations that you did back in basic algebra. Okay. Okay. So let's get in here now and make it more official. Section 1, the augmented matrix. And at the beginning, all they're having you do is convert from one form to the other. So we have a system of linear equations in 3 variables, and I want to convert it into an augmented matrix. Okay. So the way you do this is just basically pick off all the coefficients and then put a line where the equal signs are and then put 0, 5, 4 on the other side of the line. So we have 5, -2, -3, line 0. If you don't see a variable, you're going to put a 0 for its coefficient over here. Okay, so for example, I have 1, and these are the x, y's, and z's. I have 1 and then 1, and there's no z, so I'm going to put a 0. On the other side, I got a 5. Okay, then this one I have 2, 0, -3. On the other side, you put a 4. Okay, it's augmented matrix because of this line and then this other side. There's actually a kind of math where all you do is play around with this part of the matrix, and it's kind of like a big number with all kinds of information stored in it. Okay, so you can think of it as an extension of positives and negatives. So first you learn how to deal with positive numbers, and then they threw in negative numbers. So a number isn't just an amount of something. It has kind of a negative or a positive associated with it in the beginning. Now a number doesn't just have a negative or a positive associated with it. It's having like maybe 6 numbers associated with the single unit. Okay, so it becomes a special kind of math, and if you want to learn about it, take linear algebra, and they'll beat it to death there. Or just go on Google and teach yourself. All right, so anyways, let's look at going in the other direction. So you have 7, 0, 2, and then 0, 1, 7, and then 4, -5, 0, and then -13, 11, 6. Okay, so we want to convert back into our familiar form, which will be helpful at the end of this process. You'll want to convert it back and then maybe do the back substitution there. You don't always have to do that, but okay, anyways. This will be 7x plus 0y plus 4z, and then that'll equal -13. 0x plus 1y minus 5z is 11. And then 2x plus 7y plus 0z is 6. Okay, so it's pretty simple. Let's go on to the next idea. So instead of, from before when we're working with linear systems, instead of this notation, we're gonna notate it by saying times 1/2 times the equation. Instead of saying equation 1 or something, we're going to say row 1. This is where the equation is stored. So in this case, instead of saying times 1/2, we're going to say 1/2 times row 1. Okay. And you'll see instead of doing this column-wise addition method, what we're doing is kind of multiplying and then adding the rows together. So this will be another kind of operation. The third operation I hadn't shown, it's swapping rows. Okay, so you can interchange this row, and that makes total sense. It really doesn't matter which row is number 1, which row is number 2. It's not going to change any of the information about the system. So the row operations, there's 3 types. Multiply by a constant, which we're already pretty familiar with, multiplying an equation by a non-zero constant. So for example, what will that notation look like? 1/4 times equation 1. And in this case, we write row 1 instead of equation 1. Okay. The second kind of operation you're familiar with is adding two multiples of rows together, which is basically just doing the addition method for solving systems. Okay, so what will that look like? For example, -2 times row 1 plus row 3. Okay? So typically you're not going to multiply this guy by anything. It's this guy you multiply by. And then furthermore, you're storing the information, the resulting information in row 3. So that's where you put the results. Put results here. Okay. Then finally, number 3, the newer operation is just swapping rows. And our notation for that, we'll use a double-headed arrow. So if I want to swap row 1 and row 3, I'm just going to put a double-headed arrow in between, and then, just put this guy here and this guy here, that sort of thing. The entire row, though, I'm replacing one row with the other. Okay, so let's try to do one or two of these where we're applying operations. And the arithmetic that you have to do in your head is uncomfortable at first. It's kind of like relearning how to add, okay? So it's not something that I expect you to do right off the top of your head. It'll take a little practice, but it's very simple. It's not even as hard as riding a bike. It's very, very simple. Maybe you have to practice it for an hour and you have it. Anyways, the book wants you to multiply row 1 by a half, okay? So this is pretty easy. You're just going to multiply every one of these numbers by 1/2. Okay, so 2 times a half is 1. 1/2 times -6 is -3. 1/2 times 4 is 2. And then 1/2 times 10 is 5. Okay, and then leave everything else alone. And that's it. Okay, let's do some addition. It's problem 15. So we have the matrix 1, 3, 2, -3, 1, -2, 2, -1, 1, and then 0, 7, 3. And the book wants us to multiply row 1 by 3 and then add that to row 2. Okay. You can maybe notate this in your margin in the beginning, but it gets really, really nasty looking if you have numbers floating around all over the place. You want to try to be able to do it in your head. Anyways, negative row 1 plus row 2, -3 times row 1 plus row 2, you're storing the results in row 2. So row 1 and row 3 will be unchanged, and I'll just rewrite those. So then for the results of row 2, you're multiplying row 1 by -3. So I will, in this particular example, go ahead and write what that looks like. So -3 times 1, -3. -3 times -3 is 9. -3 times 2 is -6. -3 times 0 is 0. And then I'm adding that to row 2. So row 2 is right here, 3, 1, -1, 7. And then you just add it and put the results over here. Okay, so -3 plus 3 is 0. 9 plus 1 is 10. -1 plus -6 is -7. And then 0 plus 7 is 7. Okay. Let's try another one. Here's number 17. Okay. 1, 0, 2, 5. -1, 1, 0, 1, 1, -2, 3, 2, 1, -1, 4, 4, and then finally 3, 0, 11, 6. Okay, so the book wants you to do two operations this time. First, -2 times row 1 plus row 3. And then the other one, -5 times row 1 plus row 4. Okay, so row 3 and row 4 will be changed. Row 1 and row 2 will be the same. So I'm just going to rewrite row 1 and row 2. Okay. And then for these other guys, -2 times row, I'll go ahead and write it out. So -2 times this thing is -2, +2, then -2, then -2, then -6, plus row 3 is 2, 0, 3, 4, 11. Okay. So that'll give me 0, and I'm storing it in row 3, 0, 2, 1, 2, 5. Then I want to go -5 times row 1 plus row 4. So that'll be 5, -5, 5, 5, 15. And then row 4 is 5, 1, 2, 4, 6. And, whoops, this should be -5. And then this would be +5, and this would be negative, negative, and negative. So really easy to make mistakes here. -5 and 5 is 0. 5 plus 1 is 6. -5 plus 2 is -3. -5 plus 4 is -1. -15 plus 6 is -9. Okay. So there's going to be a standard procedure that we use to solve these matrices, and you know, it's one of these things that you just follow the rules and it'll give you the answer. Okay. There's two versions of it. One is just an extension of the other, so it's not like you have to memorize two different things. Okay, solving. The first one's called Gaussian Elimination, and the second one's called Gauss-Jordan Elimination. Okay. So the strategy in the first step is to get a 1 in this position. Okay, so everything else is, you know, it can be whatever. So I'll just represent the other numbers with dots. Okay. Your second objective is to get zeros below the 1. Okay, so below the 1, I want 0, 0. So you'll have 1, 0, 0, and then a bunch of junk everywhere else. Okay. My next objective is to get a 1 in this position. And the ones on this diagonal, they're going to call eventually pivot positions. Okay. Right now, we just think of this as a diagonal. And so I'd have 1, 0, 0, and then who knows, and then 1. And then I want to get a 0 below the 1. Okay, so you want to get 1s down the diagonal and 0s all below it. Okay, and they call that, well, I don't remember what they call it. It's been a while. 1, 0, 0. I think it's the lower triangle or something. I don't know. You need a 0 here, regardless of what it's called. We need a 0 below that. Okay, and then finally, I want a 1 in this last pivot position. So 1, 0, 0. Who knows? 1, 0. Who knows? Who knows? 1. Who knows? Who knows? Who knows? Okay. At this point, then you do back substitution. Once it's in this form, now back sub. So you transfer it into a system of equations and do back substitution for your answer. Okay. Going to this step here is called Gaussian elimination. I don't really care if you know the name of it, so long as you know how to do it. Okay. I mean, you're going to have to know the name for the homework. It's like when it asks you to do Gaussian elimination, this is what they're talking about. Right? But you can look that up. to do Gauss-Jordan elimination, what you're going to do is you get zeros in the top, and then you'll be able to read your answer off this last row. So some people like to do it that way. I don't really care. I think doing matrices for humans it's real easy to make errors, and it's better to just back sub into the equations for us. So that's what we're used to. Okay? But this is good for computers and later analysis of math issues. Anyways, what we're going after now is a 0 above the 1 in the middle position. Ugh. And then finally, whoops, I got a 1 here still. And then finally, you want to get zeros here. And once you've done that, that's your Gauss-Jordan elimination. Okay? So 1, 0, 0, 0, 1, 0, and then 0, 0, 1. Sometimes this is called the identity matrix, when you have zeros everywhere except ones on the diagonal. Okay? It's like the number 1, the identity. Anyways, the answer of your system will be sitting right here. So this would be like an ordered triple, your answer. And this is the Gauss-Jordan elimination. Okay, so Gauss-Jordan method. Okay, so the book's also going to call that reduced row echelon form, I believe. Okay, yeah, I think so. Okay, the book's going to start you out with some fill-in-the-blank problems, and then here, so I'll do a fill-in-the-blank, and then I'll show you doing Gauss-Jordan and Gauss-Jordan elimination as well. Okay. Okay, so there's that. Okay, so first, let's do a fill-in-the-blank. And you can see in the fill-in-the-blank, they're trying to force that Gauss elimination form. Okay. So first off, what exactly did they do in this first step? So it looks like they multiplied the first row by -2, and then they added it to row 2. And so if you multiply this by 2, well, -2, -2 plus 2 will give you the 0. Okay. All right. Then -2 times -1 is +2. +2 plus 3 is 5. Okay, so we're on track. -2 times 1 is -2, plus -1 is -3. -2 times 8 is -16, plus -2 is -18. Okay, this last row, what did I do? So it looks like I probably multiplied this by -3 and then added it to this. So -3 times row 1 and then plus row 3. Okay, so -3 times this is -3. -3 plus 3 is 0. So far so good. -3 plus times -1 is +3. 3 plus -2 is 1. -3 times 1 is -3. -3 plus -9 is -12. -3 times 8 is -24. -24 plus 9 is -15. Okay. Okay, so they got zeros below that. Now they want a 1 in this position. So it looks like they probably multiplied this by 1/5. So 1/5 times row 2. I would have 1 there. 5 times 1/5 is 1. And then -3/5. And then 1/5 times negative 18 is negative 18 fifths. And then it looks like they didn't do anything here. So this is just negative 12 and negative 15. Okay. Okay, so now let's actually try the Gaussian elimination, solve the system using Gaussian elimination. Ultimately, I don't care which method you use. Okay. So here's our matrix, our augmented matrix, sorry, 2, 1, 1, negative 1, 1, negative 2, negative 1, negative 5, 0, 4, negative 4, 4. And so what do we want to do? Well, first off, I want to get a 1 in this position. And if you could avoid having to add things together and avoid fractions, so certainly I can multiply this by 1/2, but I would introduce fractions in these two positions here, and I don't want that. It's easier to do a swap. Okay, so there is a bit of strategy here for us humans. It's easier to swap this and this, so that's what I'll do. I'll say swap row 2 and row 1. And I'll have that 1 in that position I want. So 1, 1, negative 5, negative 4. And then here I have 2, negative 1, 4. And then 1, negative 2, 0, 4. Okay, next I want to get zeros in these positions. And you're going to use this first row to accomplish that. Okay, so you're going to be multiplying things or multiplying this row by things to produce cancellations here and here. And we'll do 2 at a time, kill 2 birds with 1 stone. I want negative 2 times row 1, and then add that to row 2. And then I want negative 1 times row 1 and add that to row 3. Okay, so row 1 is unchanged, 1, 1, negative 5, and then negative 4. Row 2 then, negative 2 times 1 is negative 2, negative 2 plus 2 is 0. Negative 2 times 1 is negative 2, negative 2 plus negative 1 is negative 3. Negative 2 times negative 5 is 10. 10 plus negative 1 is 9. Negative 2 times negative 4 is positive 8. 8 plus 4 is 12. Now the third row, so negative 1 times 1 is negative 1. Negative 1 plus 1 is 0. Negative 1 times 1 is negative 1. Negative 1 plus negative 2 is negative 3. Negative 1 times negative 5 is 5. 5 plus 0 is 5. Negative 1 times negative 4 is 4. 4 plus 4 is 8. Okay. Now I want to get a 0 in this position. Oh, sorry, not a 0, but a 1. You want 1s on the diagonal. So guess what? I'm going to multiply row 2 by negative 1/3. Right? And once you get a 1 there, you can use this equation to get a 0 below it. Okay, so negative 1/3 times negative 3 is 1. Negative 1/3 times 9 is negative 3. Negative 1/3 times 12 is negative 4. Okay, now I want to get a 0 in this position. Okay, so I'll multiply row 2. I use this row now where I've created this new pivot position. I've created a 1 here in this pivot position, and I'll multiply this by 3 and add it to row 3. So 3 times row 2, and I'm adding it to row 3. Okay, so 1, 1, negative 5, and then negative 4. Okay. And then I have 0, 1, negative 3, negative 4. That row stays the same. And then multiply 3 times this row and add it to this row. So 0 times 3 is 0. 0 plus 0 is 0. 3 times 1 is 3. 3 plus negative 3 is 0. 3 times negative 3 is negative 9. Negative 9 plus 5 is negative 4. 3 times negative 4 is negative 12. Negative 12 plus 8 is negative 4 again. Finally, I need 1 in this position, and that'll close off my Gaussian elimination. Close out my Gaussian elimination. So this time I'm going to just multiply row 3 by negative 1/4. Okay, and that should do it. 1, 1, negative 5, negative 4, 0, 1, negative 3, negative 4, and then 0, 0, 1, 1. Okay, so finally then back engineer this, I guess, put it back into the system of equations. So what do I have? X plus y minus 5z is negative 4. And then y minus 3z is negative 4. And then z is 1. And you just do back substitution until you're done. So back substituting, put z into here. So you get y minus 3 times 1 is 3 equals negative 4. Add 3 the other side, y is negative 1. Now plot these two back into here, and you get x plus negative 1 is minus 1. Minus 5 times 1 is minus 5 equals negative 4. So x minus 6 is negative 4. So x is equal to 2. And we should have our solution, barring any silly mistakes. Our solution is 2, negative 1, 1. Okay? Okay, so that was the Gaussian elimination. Let's take a look now at Gauss-Jordan elimination. Okay, so let's look at a different problem, 29. We have 1, 1, 1, 2, negative 1, 1, negative 1, 1, negative 3, negative 1, 4, negative 2. Okay. It's the same game as before, it's just now instead of getting 1s on the diagonal and 0s below, I need 1 on the diagonal, 0s below, and 0s above. Okay. Okay, so let's go at it. First I need to get 0s here and here. Okay, so I'll multiply negative 1 times row 1 and add it to row 2, and then negative 1 times row 1 and add it to row 3. So row 1 is unchanged. I already have a 1 where I want it. So I have a 1 in this position. That's what I need. So I don't have to do anything with that. Okay, so negative 1 times row 1 plus row 2. So negative 1 times 1 is negative 1, plus 1 is 0. Negative 1 times 2 is negative 2, plus negative 1 is negative 3. Negative 1 times negative 1 is 1, plus 1 is 2. Negative 1 times negative 1 is 1, plus 4 is 5. Okay, let's go to this one. Negative 1 times 1 plus 1 is 0. Negative 1 times 2 is negative 2, plus 1 is negative 1. Negative 1 times negative 1 is 1, plus negative 3 is negative 2. Negative 1 times negative 1 is 1, plus negative 2 is negative 1. Okay. So now you want to get 1 in this position. So there's not much you could do, but there is a workaround. Note I have a negative 1 here. Okay? So if I swap these two and then multiplied row 2 by negative 1, I would have my result, and I've avoided fractions. Okay? So for humans, fractions are computationally difficult. So we want to avoid them when we can. You can go against me, do it your own way, but I warned you. Okay, so negative 1, negative 2, negative 1, and then so I'm swapping row 1 and 3. And then I'll have 0, negative 3, 2, and 5, and now multiply row 2 by -1. Okay, so at this point I want to get a 0 there, so I'll multiply, and you use this new row here, the second row with the 1 here, so 3 times row 2 plus row 3. So the first row is staying the same. Second row stays the same. And then the third row. So 3 times 1 is 3, plus -3 is 0. And of course, 3 times 0 is 0, plus 0 is 0 here. 3 times 2 is 6. 6 plus 2 is 8. And then 3 times 1 is 3, plus 5 is 8. And I now need a 1 in this position. So multiply row 3 by 1/8. Okay. And now I need to get zeros in the upper triangular region. So first I'll start with getting a 0 there. Okay, and I'll use the row below it. So I'm going to multiply row 2 by -2, and then add that to row 1. Okay, so row 2 and row 3 are unchanged. And then -2 times row 2. So -2 times 0 is 0, plus 1 is 1. -2 times 1 is -2. -2 plus 2 is 0. -2 times 2 is -4. -4 plus -1 is -5. -2 times 2 is -2 times 1 is -2. -2 plus -1 is -3. Okay. Now I need to get a 0 in that position and a 0 in this position. And you could use the bottom row to accomplish that. So we'll do both at once. So I need 5 times row 3 plus row 1, and then I need -2 times row 3 plus row 2. Okay, so row 3 remains unchanged this time, 0, 0, 1, 1. And then we'll go at it. So 5 times row 3, 5 times 0 is 0, 0 plus 1 is 1. 5 times 0 is 0, 0 plus 0 is 0. 5 times 1 is 5, 5 plus -5 is 0. 5 times 1 is 5, 5 plus -3 is 2. On to row 2. So -2 times 0 is 0, plus 0 is 0. -2 times 0 is 0. 0 plus 1 is 1. -2 times 1 is -2. -2 plus 2 is 0. -2 times 1 is -2. -2 plus 1 is -1. Okay, and that is your solution. So our solution is 2, -1, 1. Okay. And that's the power of Gauss-Jordan elimination as opposed to just the regular old Gaussian elimination. You don't have to do the back substitution part like you did for Gaussian. Okay. So you may prefer that. I think it's a little more dangerous, but that's just me. Okay. You can do what you want.